La 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 la. La 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 la. La 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 la. La 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 la.
Hi everyone, in this video we are going to talk about the design and the working of a potentiometer. First of all, a potentiometer is a device that is useful to compare the EMFs of two cells. So our basic purpose is we need to compare the EMFs of two cells, and of course we can also find the internal resistance of the cell, right? How do we do that? We will talk about later. First of all, if it has to compare the EMFs of two cells, it shall follow a certain principle. What is the principle is, the potential drop across a wire is directly proportional to the length of the wire that is there in a potentiometer, right? How do you get it? It's very simple. Ohm's law, V equal to IR. If I is constant, voltage is directly proportional to R. We know resistance of a wire is rho L by A. If I have a wire whose area of cross section is constant, and for a given wire specific resistance is anyway constant, potential drop is directly proportional to length. That is that simple. So we'll be having a wire where the potential drop across that wire is directly proportional to length, right? What kind of a wire that is? That's a question that I would like to answer for a while. Wire has high specific resistance and low temperature coefficient. If it has a high specific resistance, it won't get affected because of say any of the other parameters, and the low temperature coefficient means even when you vary the temperature, or even if the temperature is varied because of the experimental conditions, the nature of that wire and its resistance is not get affected seriously, right? So the kind of an example is something like manganese constant, and this kind of the wires are used, right? So we need a wire where potential drop is directly proportional to length. For that we need a very long wire, not a 1 meter wire like a meter bridge. But because of the wire is long, you cannot have a device that is very long. So what do we do is, we will divide this very long wire into meter pieces, 1 meter pieces. Say for example, you can take 10 meters wire and divide that into 10 pieces, each piece of 1 meter. So this is wire 1, this is wire 2, this is 2 meters because they are kept one upon the other. It occupies a space of only 1 meter. Now to connect these two, we can have a thin copper strip. To connect these two, we can have a thin copper strip. Again, here we can have a copper strip. Again 1 meter wire. Here also we can have a thin copper strip, and there is a 1 meter wire. Like this we can connect as many wires each of 1 meter that we need in an experiment, but they occupy a space of only 1 meter. That way we are going to have a size of only 1 meter, but this wire can be considered as a length of 1 meter plus 1 meter, 2 meter plus 3 meter plus 4 meter and so on. So a long wire is divided into 1 meter, and they are all supported with the help of connected with the help of a thin copper strip, so that their resistance is not affected seriously. So this is how you get a wire, right? So in that wire there shall be a flow of potential drop. So if you call this point as A, if you call this point as B of a long wire, I can simply show in the diagram like this, AB. So when you say AB, we are actually referring this long wire connected with the help of the copper strips. So further in the potentiometer, AB means a combination of multiple wires, each of 1 meter, but they occupy a space of only 1 meter. Now this potentiometer shall have a EMF in it, therefore it can have we can check the drop with some another EMF. So what we will have is, we'll have a cell in this circuit. This is called something like a primary cell, which is a strong EMF when compared with the EMF that you want to measure or compare. So it is strong, primary and strong, higher than that of the things that you want to compare. Of course, it can have a key where you can on and off the circuit. It can have a rheostat where you can vary the resistance, therefore you can vary the current passing in the wire. So all this part of the circuit, whatever is being mentioned, drawn here, is called something like a primary circuit. So this is always fixed, this is always there in a potentiometer. Primary circuit is always there. Whereas in a secondary circuit, we will connect a cell whose EMF you want to compare. So this is the first cell, say for example, you want to compare this. Then we will connect a galvanometer. Of course, to protect the galvanometer, a high resistance is connected in series, but that's only for the purpose of protecting galvanometer. And then it is connected with a jockey. And now this position of a jockey is kept on moving on this wire, a long wire. What's happening when a jockey is kept at a particular place is, across this length of the wire, there is a certain potential drop which is being given by this primary cell. Of course, as I told you in the beginning itself, this E is definitely greater than that of E1. That's a condition that we have. So at a particular point of the wire, through that wire of certain length, say L1, which we measure with the help of a scale, there will be a potential drop E1 which is given by this cell. And the secondary cell also there is E1, because the potential drop across the wire and the potential in the secondary circuit, this part of a circuit is called as secondary circuit, which we will modify. As both potential drops are equal, somewhere at a particular position of the jockey, this galvanometer shows zero deflection. What do you mean by galvanometer showing a zero deflection is, potential drop across the length of the wire is equal to the potential drop that we have connected in the secondary circuit, or the EMF of that secondary circuit. That implies what we can say, taking this rule into consideration, V is directly proportional to L. This V, that what we got here, is because of this E1. So E1 directly proportional to balancing length L1. Now what we do is, we remove this cell E1 and I remove that cell E1 and replace that E1 with the other cell that you want to compare, that is E2. Now let us repeat the experiment. That means what? This E2 will be passing via this jockey, and at a particular position of some other length, the potential drop across that length will be similar to that of this E2 from the primary cell. Then again the potentiometer's galvanometer shows zero deflection. In that case, you can say E2 directly proportional to L2. So dividing this and this equations, E1 by E2 equal to L1 by L2. These values of L1 and L2 we can simply calculate with the help of a scale. Thus, simply using a potentiometer, we can compare the EMF of two cells. So this is how a potentiometer designed, working, and how can you compare the EMF of two cells. So there are few primary things that you need to revise back, to remind yourself back. Wire of the potentiometer is actually shown between these 2 points is very long, but to occupy a limited space, it is cut and connected with the help of the copper strips. That's the first point. Second point, potentiometer has always two parts. This is called primary circuit. This is called as secondary circuit. Primary circuit EMF is fixed. and that is always bigger than that of the EMF that you want to compare in the secondary cell, right? So E shall be greater than E1 and E also shall be greater than E2. Then only potentiometer works. How the potentiometer works simply is, at a particular position of jockey, that is this place, potential drop across the part of the length of the wire, this one, from the primary cell E is equal to the EMF of this secondary cell E1. As potential drops across this part of the wire and due to the secondary battery are same, the galvanometer shows zero deflection. In that case, taking the potentiometer formula into consideration, we can write V directly proportional to L. So E directly proportional to L1. We'll repeat the experiment by replacing this E1 with the E2 and we'll get this. By dividing these two equations, we can compare the EMF of two cells. That's how a potentiometer is useful in comparing the EMFs of two cells. Thank you for watching.